So this next chapter then will be chapter 4, which is dynamics and Newton's laws of motion. And so Newton, there are 3 laws of motion. And so the first law, which is that an object at rest stays at rest. An object in motion stays in motion. Stays in motion unless acted upon by a net force. So basically an object will not move unless something causes it to move. So there has to be a force on it. So when you think about other objects on your table in front of you, they're not going to go anywhere unless something causes them to move. Also, in regards to the first law of motion, a lot of students in 8 o'clock morning classes have a problem with this law in that an object at rest wants to stay at rest. Newton's second law of motion, then, is a basic mathematical equation, and that is that the force is given by the mass times the acceleration. And so, again, m is the mass, which has to be in kilograms. A is the acceleration on the object, which will be in meters per second squared. And then F is the force, which is measured in terms of newtons. So really named after Isaac, this unit. Okay? So force is given by the mass times the acceleration. The third law of motion then, and one is probably more familiar with, and that is for every action there is an equal and opposite reaction. So the third law. So for every action there is an equal and opposite reaction. Equal and opposite reaction. Okay. So you fire a gun, there is the kickback on the gun, rocket goes up, propellant comes out the back, and then also if you forget your wife's birthday, then there is a reaction to that. Unfortunately, in that case, it's not equal and opposite. Well, in regards to this in forces and Newton's second law, which we had F equals ma, we can also look in terms of your weight is a force. So you stand on the bathroom scales, you're really taking your weight, which is your mass in a gravitational field. So force and weight. So from Newton's second law, we had F equals ma, but then your weight is also a force, which is given by m times g. And so in physics, you have that weight here will be measured in terms of newtons for that. Right? So in regards to this equation, you have, what is the weight to mass ratio? Over all objects. Okay. Well, we have our equation that weight is equal to the mass times gravity. And if I get the weight to mass ratio here, I divide both sides by n. We find out that the weight to mass ratio for all objects will be given by g. So the weight to mass ratio for me would be the same as the weight to mass ratio for this marker. And both of those would be equal to 9.8. Well, given this equation that weight is given the mass times gravity, we can look in terms of what would be the weight of an object here on Earth and that same object on the moon. So what is the weight? So what is the weight? Right? Right. So what is the weight of a 50 kilogram object on the Earth and moon? So we're going to use the same equation both times. So first off, the weight on the Earth will be given by the mass, which is 50, times gravity on the Earth, which is 9.8. And so this comes out to be 490 newtons. And this will be on Earth. Now we go to the moon. The weight on the moon will be 50 times the acceleration due to gravity on the moon, which is 1.6 meters per second squared. And so on the moon, the same object would have a weight of 80 newtons. So when an astronaut goes from the Earth to the moon, the mass of the astronaut doesn't change. The weight, however, does change. And that weight is dependent upon little g, and little g changes as you go from the Earth to the moon or to other planets. Well, so let's say now we have in terms of a crate on the floor, and we want to look at what forces are acting on my object. So we have a box on the floor, which has some mass, and so in terms of forces acting on this object, we have that the weight of the object will be pushing downwards. But then based on Newton's third law, we have that for every action there has to be an equal and opposite reaction, and so the box is pushing down, then at the same time the floor basically has to be pushing up. And this force is called the normal force. And normal just meaning that in the case that it is perpendicular to the surface. Now, given that this box isn't going anywhere, it's not going through the floor, and the floor is not bouncing it up into the air, we have that the sum of the forces in the y direction has to be equal to 0. Right? So, if we have that the weight of my object is in the positive direction, then the normal force would be in the negative direction, and this has to equal 0. And so we solve this for n, and so we get that the normal force here is going to just equal the weight of my object. And so we have in terms of that first scenario. But now what happens if I apply a force here? And so basically I'm now pushing on this object with some force at some angle theta. Well, what happens now in regards to our normal force? Well, again, that statement has to be true that the sum of the forces in the y direction has to be 0. So we have the weight of the object down. We also, however, have a downward component of this applied force. And that'll be given by the sign. So my forces acting in the positive direction will be the weight, the downward component of this applied force, and then in the negative direction we have the normal force, and again, the sum of those has to be equal to 0. And so again, we can take this equation and solve for n, and so all I have to do is bring n to the other side, and so we have that the normal force will be given by this. So my normal force in this scenario will be greater than the normal force in my first scenario. Well, the third possibility then, with regards to this, would be rather than pushing on the object, we are now pulling on the object. So now, the force is over on the other side. And so now my force is here, and again at some angle theta. And we want to know what happens in regards to the normal force in this scenario. Okay. Now this time, this force is also in the up direction. And so this again will be given by sine theta. And so in the positive direction, we have the weight. In the negative direction, we have the upward component of this applied force, and we also have the normal force. So again, we can solve this for n, and again all we have to do is bring the n to the other side. And so we get mg minus f sine theta is going to equal n. So the normal force has to respond to whatever the applied forces are. Right? So when the box is just laying there on the table or on the floor, we're not doing anything with it, the normal force is equal to the weight. If we are pushing on it, then the normal force has to increase in regard to that. And then if we're pulling, we have that there's a decrease due to the upward component of my applied force. So let's look at a few problems as to how all this works with regards to these various equations so far. And so the first one, want to figure out what would be the force acting on a car when it comes to a stop. So what force is exerted on a car that goes from 30 meters per second to 0 meters per second in 1.2 meters. Okay? Given the mass is 1,200 kilograms. So first off, in terms of what we know that V naught is 30 meters per second. We know the final velocity is 0 meters per second. We know the delta x is 1.2 meters. And we know the mass of my car is 1,200 kilograms. And I want to find force. Well, we have Newton's second law, which said F equals ma. Well, we have the mass, but we do not have the acceleration. But given this information, we can find the acceleration. So we have those equations from Chapter 2, one of those being that v squared equals v naught squared plus 2a delta x. So I can take that equation and I can solve it for a. So subtract v naught squared. So we get v squared minus v naught squared equals 2a delta x. Next step is to divide. So I divide both sides by 2 delta x. And so we find that a will be v squared minus v naught squared over 2 delta x. So we can take that and plug in our numbers, and so we find out that a is going to be 0 squared minus 30 squared over 2 times 1.2. And we plug that in, and that'll come out to be negative 375 meters per second squared. The negative just means what we already know, and that this car is slowing down. It's coming to a stop. So the force now is going to be the mass, which is 1,200, times 375. And so the force exerted here will be 450,000 newtons. So that would be the force exerted on my car. So whether that's through the brake or because this car ran into something and came to an abrupt stop. Well, another scenario then dealing with Newton's laws would be in terms of two masses suspended from a pole. And so basically this is a description of what is called an Atwood machine. And so I have a pulley. We have mass number 1. We have mass number 2. And maybe they're connected by a line, a wire that goes from one to the other. And so we have here that mass 1 in this case is going to be 5 kilograms, and mass number 2 here will be 7 kilograms. Okay? And I want to know, well, what forces are acting on my system. Okay? So we're going to first set up a coordinate system, and we're going to say that this way is in the positive direction. So in terms of M1, there's going to be the weight down, okay? And then there's going to be the tension in my wire up. Okay? In terms of block number 2, there's going to be the weight of this downwards. M2G. So this will be M2 times G. And then there's also this tension in the wire, which is acting that direction. Okay? Well, I know once I let this pulley and this system move, that the direction will be is that this one will go down and this one go up. So the overall motion is going to be in that direction. Okay? So what's happening here in terms of my forces? Well, let's start here on this side. Well, we got T is in the positive direction. We have the weight of the first block is in the negative direction. Okay? Over on this side, we have that this T is in the negative direction. And the weight is in the positive direction. Okay? But we also know from Newton's second law that F equals ma, and I know once I let this go that this whole system will move, and it'll move in this direction, and so this will be given by m1 plus m2 times a. So the whole system will move, and it'll all have the same acceleration, seeing that they are connected by that wire. So I want to know what is A going to be for this scenario. So what is the acceleration on this system? Right? So what will be the acceleration? And so now that we have this set up, we can find this. So we got that the T's will go away, and so we get M2G minus M1G is going to equal M1 plus M2 times A. So these two went away, and I just rearranged these into the opposite order. Okay. Well, on this side, I can take out a G, and so we get M2 minus M1 times G equals M1 plus M2 times A. And I'm going to solve this for A, so the next step is to divide. So divide both sides by M1 plus M2. And we end up with our equation, which says that the acceleration will be given by the difference in the masses divided by the sum of the masses times G. Okay. So now we can take our numbers and we can plug this in, and so we get 7 minus 5 over 5 plus 7 times 9.8. So we end up with 2 over 12 times 9.8, and we get an acceleration here of A of 1.63 meters per second squared. Will be the acceleration on my object. So you got that if both objects actually weigh the same, then this thing goes nowhere, okay? Because then if you look at this equation, this top term would be 0. And then when you get to where m2 is much, much greater than m1, you could end up going towards the extreme, which would be free fall. Okay? Well, in terms of forces acting on the system, the other force that can act on the system then is friction. And so friction is a force which acts in the opposite direction of motion. And so there are 2 types of friction. And those 2 types are static and kinetic. So there's static friction, and then there is kinetic friction. And the 2 equations for those are, you get F sub S, S sub S has to be greater than or equal to mu sub S times N, and then F sub K is going to be mu sub K times N. Okay? So this is the coefficient of static friction. And so you can find tables with this data. Basically, it's all dependent upon what 2 surfaces are in contact with each other. And then this would be the coefficient of kinetic friction. So those numbers are constant. And then in the case of both equations, you have that N here is the normal force. Okay? And the way it works is that mu sub S will be greater than mu sub K. So you can think about it. If you think about pushing a heavy piece of furniture across the floor, that it takes more effort to get it going than to keep it moving once you start. So eventually you have to get over this coefficient of static friction first, and then once you got it going, you can let off a little bit, and it's a bit easier to move. So friction can be a good thing. One of the ways you see that is in the wintertime, you get those news stories out of Seattle, and they show the cars going down the various hills when they're covered with snow and ice, and the cars just sort of slide down the hill, bouncing off the cars that are parked on the side of the road. So friction can be a good thing, and the type of friction that comes into play with your car when you're driving is actually going to be this friction and not kinetic, because this is the one you want. This is greater. And the reason why this happens to be static friction in regards to your car is if you think about your tires and you're going down the road and you're traveling in this direction, is basically I need to get this piece moving, and then once I move that piece, I now have a new piece, a new surface that's on the road, and I now have to get that going. And so it's static friction that comes into play when you're driving. Right? Kinetic friction you don't want, because that would mean that at that point in your car is sliding down the road, and that is not a good thing. Right? So in regards to a question dealing with this stuff, so let's say we now have this scenario. I have a box. We have an applied force here at an angle of 25 degrees. And the box weighs 40, has a mass of 40 kilograms. And I want to know how much force is needed to start the box moving, given that mu sub s is equal to 0.62. Okay. So in regards to the forces that are acting on my system here, we've got that there is a downward component due to this applied force, which will be given by F sine theta. There is the weight of this, so there is mg here. There also is a normal force, which is acting here. Okay? But then in terms of getting this box moving, there is this part of this applied force which is in the direction I want, which will be given by that. Okay? So we have that F sub s is going to be given by mu sub s times n, which has to be greater than or equal to this, which means basically in order to get an object moving, if I'm at the number it goes nowhere, I basically have to beat that number by just a little bit, then it goes. So my applied force that's driving this down the road is going to be given by F cosine theta. And that is going to be equal to mu sub s times n. And so mu sub s, and the n in this case, if you go back to the scenarios we have with the boxes and the three different scenarios, we had from there that this will be given by mg plus F sine theta. So the normal force has to balance out the weight plus this part of the applied force. So now we can take all our numbers and start plugging this in, and so we get F cosine 25 equals 0.62 40 times 9.8 plus F sine of 25. And so we number crunch this out. We get 0.906F equals 0.62 times 392 plus 0.423F. Next thing I'm going to do is take care of my distributive property. And so we'll do 0.62 times those, and this will be 243.04 plus 0.26226F. Again, I want to solve for F, so now I want to take this to the other side. So I will subtract and subtract over here. Sorry, so let's get the number right. So 0.26226F. And when I do that, this will become 0.64374F equals 243.04. Last step is to divide. And so we end up that the applied force here will be 378 newtons. And basically that's the break-even point. So really if I want to get this going, I have to beat that number and then it moves. Okay? And then if I knew what mu sub k is, I could go through this whole thing again. All I have to do is switch this number out and we could get how much force would be needed to keep it moving, given we know a mu sub k value. And with that, that will wrap up the discussion from Chapter 4 and Newton's laws of motion. Thank you.